Talking about problem reductions. So we saw last week a bunch of failure detectors, eventually P, and some other ones. And we saw also linear election and eventual linear election. So these are all problems, and you can make algorithms for them. But we want to make connections between them. So I'm going to talk first a little bit of mathematics about problem reductions. So we're going to introduce a few definitions. So you say x is reducible to y with this symbol here. It's kind of like less than or equal. If x is a problem, such as some algorithm, maybe broadcast or consensus or whatever. So if I have an algorithm to do y, I can use it to solve x. X can be solved given a solution of y. X is reducible to y. So that is a definition of how problems are connected. So x is not harder than y. It's easier, or maybe as hard as y, but not harder. Because if you have an algorithm for y, you can use it to solve x. Okay? So that's the notion of reductions. X is reducible to y. So we're going to try to connect some of the things we know using this. So first of all, we want to investigate this thing. So this is actually what's called a pre-order on the set. So a relation here I mark it by a tilde, is a pre-order if x is related to x, and if there's transitivity. X related to y, yz implies xz. So all you need is that a relation is reflexive with respect to itself and it's transitive. So this is not the same as a partial order. So this is a pre-order. A partial order is more. A partial order says that if x is related to y and y related to x, then x is equal to y. So like for integers, if x is less than or equal to y is less than or equal to x, then x is equal to y. That they're the same thing. But pre-order, it's not like that. We can have a symmetry even for different things. So problem reduction is actually a pre-order. So it's not exactly like partial order. So it's reflexive. X can be solved given a solution to x. That's pretty clear. And it's transitive. So x can be solved given a solution to y, and y can be solved with z, implies x can be solved with z. So basically you use the implementation of z to implement y, and then use that implementation to implement x. So it's transitive. Okay? But it's not a partial order. If x can be solved by y, and y can be solved by x, then it does not mean that they're the same problem. Huh? They're equivalent problems. So if x can be solved by y and y by x, it does not mean they're the same problem. It just means that they're equivalent to each other. You can solve one with the other. So this is why it's not partial order. Okay? So this connection, this pre-order connection between problems is really useful in distributed systems. Because we're going to be comparing problems to each other. Okay? So some notation, x is equivalent to y if x can be reduced to y and y can be reduced to x. So it means that they're just as strong as each other. You can do one with the other, but maybe they're not the same. They're not necessarily exactly the same. Huh? Remember we talked about consensus and total order broadcast in the first course? Well, they're equivalent, but they're not the same problem. Okay? And x is strictly weaker than y. That means x can strictly not be reduced to y. if x is strictly weaker, if x can be reduced to y, but it's not equivalent. That means it's actually weak, it's really weaker. You can use y to do x, but it's not, they're not the same, okay? Or you can say y is strictly stronger than x. That means y is stronger, so you can use y to implement x, but not the other direction, okay? X can be reduced to y, and y is not reducible to x, okay? So this makes like a strict comparison between the two. So you can see there's different kinds of comparisons. There's x is reducible to y, x is strictly weaker than y, or x is equivalent to y. So there's different ways to compare problems. Okay? So we already know a little bit of that. For example, eventually p is reducible to p. That means given p, we can implement eventually p. That's easy, huh? You just return the results of p and say it's the results of eventually p. And eventually p is allowed to make mistakes for a while. P does not make mistakes. But it's okay if p is okay for eventually p. Because eventually p does not have to make mistakes. Huh? P is like a version that doesn't make mistakes. P always satisfies eventually p's properties. So it never makes mistakes. So the time period that it makes mistakes is empty. But that's okay. We already saw also that eventually p is strictly weaker than p. They're not equivalent, actually. You can implement eventually p with p, but you can't do the opposite. If I have in the asynchronous model, if I have eventually p, it's allowed to make mistakes. P doesn't make mistakes. But I cannot reduce p to eventually p. If I have an algorithm that sometimes makes mistakes, I can't get rid of those mistakes. Okay? There's no way I can tell if it's a mistake or not. So I cannot reduce implement p with eventually p. Okay? So that's an easy way to write it. You can say eventually p is strictly weaker because making mistakes is really something different than not making mistakes. Okay? So this is a nice compact way of comparing problems. So for example, if x is reducible to y, and if x is impossible, if we know there's no algorithm to solve this problem, then also y has to be impossible. Because if y were not impossible, we could use y to implement x. So this is, we can make a reasoning like this. If x is reducible to y, and x is impossible, then y is impossible. Okay? So that's nice. We can talk about it, but it's nice to have this compact notation. Okay? Or for example, eventually p can be reduced to p. If we can solve a problem with eventually p, we can also solve it with p because of the transitivity. It's easy. If you can solve it with a failure detector that's allowed to make mistakes, then you can also solve it with a failure detector that makes no mistakes. Okay? So this is because of the transitivity. You see, so it's kind of a very quick, compact way of talking about the strength of the different problems. Especially for us, it's really important. We're going to be comparing these two, eventually p and p, throughout the whole course. Okay? We're going to be talking about these different problems. Okay, so one important question. So let's say we use p to solve a problem. Okay? We have an algorithm and it uses p, perfect failure detector. So that's nice, but p is actually not very practical. P is actually really hard to implement. It's actually impossible for implement. You need synchrony. So one important question is to see whether x is practical. Can we implement x with eventually p? Sometimes it's not possible. Sometimes it is. So eventually p is strictly weaker than p. Can we implement x with eventually p? Sometimes we can reason using the reductions. So for example, let's say that x is solvable with p, okay? And we want to see whether x can be solved with a weaker failure detector, eventually p. Or maybe it's impossible. Maybe eventually p is strictly weaker than x, okay? And that means you can use x to solve eventually p, but you cannot use eventually p to solve x, okay? So we can actually do proofs like this, okay? Let's say we want to prove that p is the weakest failure detector for solving x, okay? Now if we prove that p is reducible to x, that means we can use x to solve p, okay? If p is reducible to x, we also know that eventually p is strictly weaker than x, okay? So if we were able to solve x with a weaker failure detector, then we could solve p with eventually p, okay? So that's not possible. You cannot solve p with eventually p. You cannot get rid of the mistakes. But if we can solve x with eventually p, then we would have this. We can solve x with eventually p, and we know that eventually p is strictly weaker than p, p. Then let's see. Am I writing it right? No, I'm not writing it right. See, it's kind of subtle. So basically, eventually p is strictly weaker than p. Okay. Let's say we want to see whether we can solve x with a weaker failure detector than p. If this were possible, if you could solve x with a weaker failure detector than p, then x would be equivalent to eventually p, and you could solve p with eventually p. So that's a contradiction. So you can reason about this kind of things, okay? So with this, I want to play a little game now. I want to play a game and connect the detectors we saw before. So we saw a bunch of detectors, strong detector, eventually strong. We saw P, eventually P. So we saw a bunch of them. So I just want to play a game, and that's just to get some practice in thinking about how these problems connect to each other, okay? In order to do that, let me first set the stage. Let me first refresh your memory about the different meanings. So we have completeness and accuracy. Okay, so for completeness we have strong completeness and weak completeness. Accuracy we have strong accuracy and weak accuracy. So I'm just going to refresh here so that we can talk about the different possibilities. So strong completeness means that every crash node is eventually detected by all correct nodes. Okay? Crash detected by all correct nodes. Okay? So that's strong completeness. Weak completeness is the crash is detected by some correct node. Some correct node. basically there's some node which is really smart, or which has a really good connection to all the other nodes, so it's able to see all the crashes. But maybe the other nodes are not able to see the crashes. So the example I gave is like you have a football field, and you have somebody standing on the field, and you have all the participants. So the guy standing on the field can see with a telescope whether anybody has fainted in the bleachers, okay? You can see that. But the guys in the bleachers cannot see each other. It's kind of hard to see each other in the bleachers. Because there's people below, above, so it's hard. But the guy on the field can see everybody. So this is an example of weak completeness, okay? And also we have strong accuracy and weak accuracy. So accuracy is whether we have mistakes. So correct node, no correct node is suspected, ever. Okay, that's strong accuracy. Weak accuracy, there is some correct node is never suspected. So there is some correct node and you never make mistakes with respect to that one. But you can always make mistakes maybe with respect to other nodes. But you always have a good view. There exists a correct node which is never suspected by any node. So you can use the football field analogy, yeah? If there's a guy on the field, everybody can see whether that guy is fainting or not. Boom, it's very easy. So that node, and if that guy does not faint, everybody knows it. So if the guy is not fainting on the field, then we have weak accuracy. Because maybe they make mistakes with respect to each other, but they will not make a mistake with respect to the guy on the field. Okay? So this is important. The different degrees. Strong, weak, complete, strong, weak, accuracy. It's really important because the differences might seem small, but it makes a big difference when we want to build systems. Okay? So now we saw a whole bunch of failure detectors. So we saw, let's start with the easy ones. Eventually P and P. So eventually P is eventually strongly accurate. That means it makes mistakes in the beginning, but eventually it stops making mistakes. And P never makes mistakes. So eventually P can be reduced to P. So this arrow is the reduction. Okay? See, so that's easy, right? Remember we had also this S, this funny S detector, which is called strong for weird reasons because distributed systems, people were completely messed up in the 90s, in the 1990s, and that's when they invented this thing. So they called it strong, but it's actually not as strong as P. Yeah? So the S detector is weakly accurate. Okay? That means there's some special node that it works really well with. It never suspects it. So the S detector is weakly accurate. But we can also have eventually S. That means in the beginning it can make mistakes with respect to everybody, but after some time it never makes mistakes. There's one guy that it stops making mistakes for. Okay? See, it's a little bit subtle, huh? So the eventually S can be reduced to S, of course, because eventually S makes mistakes with respect to everybody, but S makes, for a while, but S and never makes mistakes with respect to one person after that, but S never makes mistakes with respect to that one guy, okay? A little bit subtle. So we can make reductions. But we can also make other reductions. So S and P. So P is strongly accurate and S is weakly accurate. So P never makes mistakes. at all. Okay? But S is allowed to make mistakes with everybody except for one guy. So S can be reduced to P, because S makes some mistakes, P never makes any mistakes. So we can reduce S to P. And we can also reduce eventually S to eventually P. Oof. It's like a puzzle, huh? Okay? Okay? So these are reductions that we can do. These are actually very simple, huh? Trivial reductions, because you can see them right away from the definition. Huh? You remember that there's also these other detectors, which are the weak complete detectors. So Q is weak, is weakly complete. That means not everybody sees the crashes. Q never makes mistakes, but not everybody sees the crashes. Only some nodes see the crashes, okay? And eventually Q means it's actually allowed to make mistakes. And eventually it never makes mistakes, but still it doesn't see all the crashes. I mean, only some nodes see all the crashes, okay? And then there's this W detector, which is called the weak detector for some weird name, some weird reason. So this one is a weakly accurate version of Q, weakly accurate, okay? Which means that it makes mistakes with respect to everybody except one guy. It doesn't make mistakes with respect to that guy. And the eventually weak accurate makes mistakes with respect to everybody, but eventually it stops making mistakes with respect to one guy. Okay? So you can also make reductions, and then you can make reductions from between strongly accurate and weakly accurate. Okay? And you can make reduction between eventually strongly accurate and eventually weakly accurate. It's an interesting game, huh? Lots of specification here. Okay, now we can connect these two diagrams. Okay, we have this diagram here, which I will put here. So the strongly complete diagram. And then we have the weakly complete diagram. So the weakly complete diagram, let me put it here. Oops. So we have Q. Don't worry, things will simplify. This is just an exercise to get you familiar with the things, but at the end of the day, most of these detectors, we're not going to use them anymore. Okay, so here we have the strongly complete diagram. Here's the weakly complete diagram. So we have these two diagrams. The strongly complete means that all nodes will detect the crashes, and weakly complete, some nodes will detect the crashes. Now it turns out, in the 90s, all these detectors people were working on all these detectors. It turns out that the weak and the strong completeness, you can actually reduce them to each other. That it doesn't really make any difference, the strong and the weak completeness. So they're actually equivalent. A detector that's weakly complete, a detector that's strongly complete, it's actually equivalent. And we can prove that. Okay? We can prove it in both directions. So the first direction, of course, weak completeness is trivially reducible to strong. Huh? If everybody can see all the crashes, then of course some of them can see it because everybody can see it. Okay, so that direction is easy. The other direction is also possible. Okay? We can reduce strong completeness to weak. That means if you have weak completeness, you can actually make strong completeness. So how do you do that? And that means that all of these guys are equivalent. P and Q, S and W, and these two. How can you reduce strong completeness to weak? Okay, it means if we have weak completeness, can we implement strong completeness? So weak completeness is some correct node detects all the crashes. So how do we make it strong? Actually, it's pretty easy. The weak node just has to broadcast that information. This node, sorry, the one that always detects it, says, I think this node is crashed. But maybe the other node doesn't know that. I'll just broadcast it to that node. Okay? And then all nodes will detect it. Every node broadcasts suspicions periodically. Okay? So every node, when it has a suspicion of a crash, it broadcasts that to everybody else. That means this one node that sees all the crashes will send that information to everybody. Okay? And when a node receives this broadcast, it adds S, the nodes, to the suspicions, but it also removes Q, because the node that it received things from, which is clearly working. Okay? So you're like disseminating the information. But you have to make sure that this doesn't break the accuracy. Okay? You're disseminating information about crashes from this one node to all of the nodes, but you have to make sure it doesn't break the accuracy. Okay? So, if we do this, every crash is eventually detected by all correct P, because the suspicions are going to be broadcast to everybody. But we have to make sure that this doesn't add mistakes. So the accuracy is the mistakes. Can it violate accuracy? But actually it doesn't. Neither it does strong, neither weak. We reason about it, we can see the accuracy is not violated. So strong accuracy means never any mistakes. Okay, never any mistakes. Well, that means the node that's broadcasting the information will never broadcast mistakes. It's pretty clear, right? Because nobody's making mistakes. So strong accuracy is okay. It will never spread inaccurate suspicions. What about weak accuracy? Well, weak accuracy means that there's some correct node never suspected by anybody. Well, that means the node that's broadcasting that information will not suspect that node either. So nobody ever suspects that correct node, so the broadcast will not change that. Because nobody suspects it, that information is not going to change. So weak accuracy is not violated either. Okay? What it basically means is that, in the eventual cases it's also proved, you can, if you have eventual strong accuracy, eventual weak accuracy, you can also prove that it won't be any problem, because eventually means you're allowed to make mistakes for a certain time. So if you think about it, you can show that it works also. So basically what that means is that in this diagram, the arrows mean reducible to. So here we have the strong complete cube, the diamond, and here we have the weak complete diamond. And these corresponding ones are actually equivalent problems. Okay? One can be reducible to the other. So that actually explains all of the research on failure detectors, or most of it, from the 1990s. A lot of people worked hard, and you can see how actually, if you present it in the right way, it's not such a big deal. Okay? And for all these failure detectors, we're only going to be using a few of them in the course. Okay? Okay, I'm not going to talk about, oh my God, let me skip this slide. This one. This is going a little too much in detail, I think. I'm not going to talk about the CHT theorem. Okay? So, this basically connects all of these failure detectors together. But in the rest of the course, we're not actually going to look at all those failure detectors. Okay? We're only going to look at some of them. Basically, we're going to look at the following things. We're going to look at the case when you have perfect failure detectors. So basically, crash stop. So we're going to look at crash stop and perfect failure detectors. And this is called fail stop. Now, fail stop means that you can get crashes and you can perfectly detect them. Now, fail silent means you have crash stop but you have no failure detector. And fail noisy means you have crash stop and you have an eventually perfect failure detector. Actually, it means fail stop is basically synchronous. You have a perfect failure detector. Fail silent. Nodes fail, but nobody knows. That actually corresponds to asynchronous. Okay? And because you can't know failures in asynchronous, and fail noisy means you're allowed to make mistakes for a while, but then you stop making mistakes. So that corresponds to partially synchronous. Okay? So these are the ones we're mostly going to talk about. So the most of the time we're going to talk about P and eventually P. A little bit about S and eventually S, and we're never going to talk about those other ones. Okay? So one of the important things in this course is that we're going to go from P to eventually P. Assume crash stop with a perfect failure detector. It's a very nice, simple model. We're going to make algorithms for that. Okay? And then we're going to say, well, maybe we want to change the perfect failure detector and make it eventual. But that makes it practical, because P is not really practical, but the algorithms are easy. But here, eventually P makes it practical. Is it possible to take these algorithms and twiddle them a little bit so they still work? So giving algorithms for P and seeing whether we can make them work for eventually P. Sometimes it works, sometimes it doesn't work. Okay. So this is actually summarizing a lot of the course from P to eventually P. Okay. So most of these detectors, you can forget about them. In fact, we were just playing this game to give you some experience in thinking about all these properties, okay? You have to understand the properties. But in terms of the actual failure detectors, most of the time we're going to use P and eventually P. Sometimes we're going to use this strong detector. Sometimes actually the strong detector, where there's one node here detecting they can see all the failures. Sometimes that's good, but we're never going to use those other ones. Okay. Okay. So that's for failure detectors. But now we're going to start doing algorithms. Okay. So we're going to go down from the abstract to mathematical part, and we're going to see some algorithms. And we're going to start with broadcast algorithms.